The great news for astronomers is that nowadays we do have access to pretty much all wavelengths, and we can actually explore them to learn a lot about astronomical objects. In this figure, you're essentially just seeing some indication of the frequency and the wavelength of what we'd call radio waves, then microwaves, into the infrared that you can see here, into also the optical, where our eyes are sensitive to, then going to the ultraviolet, X-rays, and gamma rays. And some of the arrows you will see, they actually overlap a little bit, especially here. And that is mostly because sometimes the definitions kind of overlapped, and what we call X-rays and gamma rays might be relatively the same thing, but in general, X-rays will be less energetic than gamma rays. Now, an important thing to consider is that even though we have instruments and we can gather information from all these wavelengths or frequencies, doing it from the ground has a lot of limitations. And that is because the Earth's opacity actually is quite high for some of the wavelengths. And this is one of the things that we're going to see next. In the figure above that we can have a look at, what you're seeing is a transparency of the Earth's atmosphere versus the wavelength at which you're observing. And it's really quite clear that, especially at the shortest wavelengths or highest frequencies, Earth's atmosphere is particularly opaque. This means we cannot see the UV, X-rays, and the highest energy photons like gamma rays. The reason for it is explained here. This is because at those energies, when those photons get to the atmosphere, they very easily excite or even ionize atoms and molecules in our atmosphere. And therefore, if we want to gain some information in the ultraviolet or X-rays, we do need to typically place telescopes above the atmosphere, at least above the layer that is actually collecting these photons and ionizing or exciting. For those of you that have been able to see an amazing dark sky, we know that the atmosphere is particularly transparent in the optical window, as you can see here. This is the reason why a lot of the telescopes from the ground function at those wavelengths. The only problem is, of course, if you're living in Lancaster or most places in England, where clouds can actually absorb a lot of the optical photons. So there's a big attenuation. But fortunately, apart from the clouds, then astronomers get the optical pretty much covered. Now, when we move to the near-infrared, and in the beginning, I told you that we typically split the infrared into the near-infrared, mid-infrared, and far-infrared. The near-infrared is a region around 1 to 2 microns, where the atmosphere is still relatively transparent in specific bands. You'll see that there are some reds where the atmosphere is transparent, and then some blue where it is not. These are actually named, these bands, and those that astronomers use a lot are called Y, J, H, and K. Now, the reason why some bands are not transparent is because these infrared photons have just the right energy to actually excite molecules in the atmosphere, because they match the rotational and also vibrational states of molecules. So they excite them, and therefore we cannot see them directly. But it is important to point out, as shown here, that some bands are relatively unaffected, and they're used a lot from the ground. Now, the problem is when we move to even longer wavelengths, there is a big gap here where the atmosphere is completely opaque. So in the mid-infrared, there's a little bit of a gap. In the far-infrared, it's completely gone. And this holds until sort of the region of microwaves. And in the microwave regime, it's not surprising that the atmosphere is also not transparent, because there's water in the atmosphere. So just like your microwave works at home by exciting water molecules, then any microwaves coming down to Earth will excite the molecules in the Earth's atmosphere, and we will not be able to see them. So the reason why the far infrared and then some of the microwaves are completely blocked is because these photons have the correct energy to excite things like water and also other molecules. Finally, in the radio, actually, the atmosphere is quite transparent. This is even the case from the lowest altitudes. This is the reason why the UK can still have some amazing radio telescopes, or the Netherlands, because in the radio frequencies Photons don't care about clouds. They're too big for the typical sizes of the particles. And this means that we can do radio astronomy between something like a few centimeters for the wavelength up to something like 10 meters. Above that, as you can see here, the atmosphere becomes opaque again.